Hello everyone and welcome back to the channel. This sequence of videos we are going to cover dynamic programming. This is another programming paradigm where we solve some of the more complex problems which cannot be easily solved by other methods we have looked. For instance, greedy solutions or divide and conquer solutions. Those solutions generally does not work on these set of problems, or even if they work, it is going to take a lot of processing to find a solution. So at a high level, what dynamic programming does is it finds subproblems, solve them, and keep the solution in memory so that it does not have to solve those subproblems which are already solved. So those subproblems which are already solved and which have a solution already found and is saved, then this saves time by just looking up the solution for a specific subproblem and not calculate the subproblem again. This is the whole idea of dynamic programming. Dynamic programming is mostly iterative, where it builds a grid and keeps solving the subproblems and filling the grid with the solutions. And eventually at the end, it finds the final solution. That's how dynamic programming works at a high level. As we go, you will have more better understanding of how this paradigm works. Before we dive into a problem, let's see the basic steps of dynamic programming. So the first step is finding a optimal substructure of the problem. Identify optimal substructure, which means you try to find subproblems in the main problem. Then you define a recurrence for these subproblems. Solve the recurrence to find solutions to subproblems. And while solving the subproblems, we eventually reach to the final solution. And then we reconstruct the solution. So these are the four basic steps of a dynamic programming solution. So before we dive into more complex problems which are generally solved by dynamic programming, like knapsack problem or the traveling salesman problem, we are going to look at a very simple problem to gives you a hands-on on how dynamic programming is going to work. So let's say I have a line graph, and these are the values or weights. What we have to do is we have to find the maximum weighted sum of the vertices, and the condition is two vertices cannot be adjacent. So this means we can take one, we can take second vertex, we can take third vertex, we can take fourth vertex, or we can take first and third vertex, we can take second and fourth vertex, and we can take first and fourth vertex. But we cannot take first or second vertex, or we cannot take second or third vertex, or third or fourth vertex, because these are adjacent. So because this is a small graph, we can quickly see that the solution is second and fourth vertex, which gives us the maximum weighted sum of 8. Other combinations, if let's say we take this, it's going to be 6. Or if we are going to take this and this is going to be 5. So the answer is second and fourth vertex. Now, how we can solve this problem? Let's see. So we have 4 vertices, v1, v2, v3, and v4, and the weights are 1, 4, 5, 4. Okay. Let's say we create an array or a grid of n plus 1 indexes. So this is 0, 1, 2, 3, 4. Okay. Which represents vertex 1, vertex 2, vertex 3, vertex 4. Now, let's say in the 0th index, I am going to put a 0, and at the first vertex, I am going to put a value of vertex 1. Okay. Now, what is going to be the value at index 2? The value at this index would be either this, because this could be greater, or it could be value of index this and value of vertex 2, right? Because either the maximum value could be at the previous index. So we are here, the maximum value could be at the previous index, which is v1, or because we have to take 2 vertices which are not adjacent, then if we are counting v1, v2, then we cannot sum v1 into v2. So the non-adjacent vertex is this. So either we sum this and this, or we take the previous one. So previous one is 1, or it could be 0 plus whatever is the maximum. So 0 is the previous to previous index and the weight at the current vertex. So this came out to be 4 because 4 is greater, right? Okay. Same, if now we want to put a value here, the maximum we have seen so far, then it could be either 4, which is the previous. So this value is going to carry forward to vertex 3 index, or it could be sum of these two, right? So try to understand, either the maximum value could be at the previous index, which is the second index because we are currently at 3, or it could be sum of index 1 plus value at vertex 3. So it could be 4, which came from here, or it could be this one and sum of this one. So this is 1 plus 5. So we see that the maximum came out to be 6. So we put 6 here. Similarly, when we are here, the maximum value either can come from the previous vertex, or it could come from already calculated maximum and the current weight. So you see how we are using the previous calculations for our current solution to the subproblem. So like we have already calculated what would be the maximum weight for index 3, and we have already calculated what would be the maximum weight at vertex 2, right? And we are not doing all these calculations again and again. This way, dynamic programming is building a grid and keeping the sub solutions in the grid so that those can be reused again and again. So now if we see that the previous index is value is 6, or it could come from the previous to previous index and the current weight at the 4th vertex. So this will be 4 plus 4, which is 8, and we put a 8 here, and that's our answer. So the maximum weighted sum for this graph is 8, and I think we already looked at it. The maximum weighted sum was 8. So what we are doing, we are either taking the previous index, or we are taking the previous to previous index plus the weight of the ith vertex. So we have already found the subproblems which are actually the vertices in the graph. So the first step is, vertices are the subproblems. 2, finding a recurrence. So going by the same logic, if we have to find the recurrence for this, what we did is, initially at index 0 of the array we put 0, at first index we put value at vertex 1. Okay, after that we do a for loop from 1 to n, and at every index what we did is, either we picked the index which was 1 less than I, so then maximum of I minus 1, or we picked value at index I minus 2 plus weight of current vertex, and that created our recurrence. Then the third step was to solve this recurrence and find solutions to the subproblems, which we did by filling up the grid. Then the fourth step is, now we already know that the answer to this problem is 8, but we don't know what all vertices were part of the solution. Although this is a small problem, so we already know that the vertex 2 and vertex 4 was part of the solution. But how are we going to find that out? So if we look at our grid, the final grid, which was 0, 1, 4, 6, 8. Okay. Now looking at index I, 3, 4, starting from n to 1, this 8 would either come from the previous index or this weight would either be coming from this plus value of 4, right? So this means either it is coming from I minus 1, which is 6, or it is coming from I minus 2 plus weight of 4, which is 4 plus 4. And we always pick the maximum value out of these two. So we see that the maximum value is coming from this one, which means we must have picked vertex 4 and must have added value at index 2, right? So then vertex 4 is part of our solution. So if we say solution set, vertex 4 is our solution set. This means 6 is not going to be part of our solution set because this is going to be the adjacent vertex to vertex 4. So then we should be going here straight away because 6 is not part of the solution. Now, what are the possibilities? Either 4 could be part of solution, 1 could be part of solution, right? So we reach here. So then what we did is I is equal to I minus 2. And then we again do the same thing. So either this 4 came from the previous vertex, I minus 1, I is equal to 2, which is which is 1, or this 4 came from previous to previous vertex value plus weight of vertex 2. Which is 0 plus 4. So this is smaller. Definitely we did not pick it. We must have picked this, which means vertex 2 was picked for the solution. So we add vertex 2 and we again do I is equal to I minus 2, which makes it I is equal to 0. And if we reach I equal to 0, this is our dummy index and we are going to stop the iteration. So that's how we reconstructed our solution, that vertex 4 and vertex 2 were part of the solution. So if we need to write code for this is going to be pretty simple. How? We create a solution set which is empty. In the beginning, we do a for loop, I is equal to n to 1, and we see where the value came from. So if I minus 1 is greater than plus value at I, then we must have picked this, and from here, so let's say we are here, and if we have picked this, then we must not have picked this, and this value actually must have been carried forward. So this is not a solution, and probably this could be our solution. So we will move here and see where this 6 came from. Now this 6 either would be part of the solution, or this 6 might have been carried forward from the previous one. So in this case, we are not going to add 8 to the solution set or the vertex 4 to the solution set, because we know that 8 is not part of the solution, because I minus 1 is greater. So what we do is I is equal to I minus 1, right? And then we again see if 6 is part of the solution or it is carried forward from the previous index. Else, if the previous index is not greater, then this means this was greater, or we saw here, if this was greater, we had picked these vertices. So then this means add to S and I is equal to I minus 2, right? So if vertex 4 is part of the solution, then add vertex 4 to the solution and move 2 spaces back. And in the end, return S. This is your code for reconstructing the solution. So this is a very high level introduction to dynamic programming, where I showed you a very basic problem and the idea of how dynamic programming creates a grid of subsolutions and use those subsolutions to reach a final answer. And if we just need the final answer, the 4th step is not required. But if the answer also needs the sub solutions to sub problems, then we need to reconstruct the solution, which is step 4. With this information, I'm going to end this session here, and I am going to see you in our next session, where I am going to discuss knapsack 01 problem and solve it using the dynamic programming paradigm. Until then, bye for now, and thanks for watching.